Hey everybody, welcome to today's lesson. Today we're going to be continuing our 3-day discussion. This is day number 3 of intermolecular forces. So again, just a quick reminder, if you haven't already watched my other 2 videos, you should go back and watch those first. But intermolecular forces, again, are those attractive forces that exist between molecules. And they help us explain why certain substances exist as solids versus liquids versus gases. So what we're going to be talking about today is a specialty intermolecular force called hydrogen bonding. I do want to clarify that hydrogen bonding, even though it contains the word bond in it, it is not considered a bond, right? It's not like covalent bond or ionic bond. It is an intermolecular force of attraction. So hence why in my guided notes sheet, if you do use those, it does say not a bond up top. So in order to kind of bring you or to kind of point out why this is so impressive or why it has to be considered a specialty intermolecular force, I did want to just take a quick look at this graph that I have here on the screen and on the guided notes sheet. So notice that we have here a series of boiling points based on the molecular mass, okay? And before we dig into kind of what's interesting about this, I want to go ahead and just draw all those structures out, and that'll kind of help us explain why it's so fascinating. So notice that these molecules are all made from H or hydrogen along with a group 16 atom. So we have H2O, okay, and remember that when we do draw these group 16 atoms, we do draw them in this shape. Okay, we have H2S. We have H2TE. Oops, I skipped one. And we have H2SE. Okay, and so looking at these, there is no real profound reason by looking at these that there should be any significant difference really in their boiling points. Based on what we've discussed so far, all of these, their primary force of attraction, right, should be dipole-dipole because they're all considered polar molecules, okay? So when we then start to compare boiling points or the strength of the intermolecular forces, if they all contain the same type of primary intermolecular force, we then need to compare the London dispersion forces or the molar masses. So if you were to consider the molar masses, right, you really only need to look at the O, the S, the SE, and the TE. And you don't really need to even look too closely because if you think about the organization of group 16, we have O, S, SE, and TE. And we know that as we go down the group, we do have an increased number of electrons. So looking at our graph that's been provided here, okay, we do see an increased number of electrons or an increased molar mass as long as we flip these two, okay? And so we see that increase, and therefore we should see an increase in the boiling point or an increase in the strength of those intermolecular forces. So you'll notice on the graph, going back to that now, that there were the projected boiling point for water was actually significantly lower, and as it should be based on what we know thus far about intermolecular forces. Water is in fact the smallest of these 4 molecules. It has the theoretical weakest intermolecular forces, but you'll notice that water's boiling point is actually way up here, and that's really surprising, right? So since H2O has the lowest molar mass or gram formula mass, it is expected to have the lowest boiling point or the weakest forces. But this graph and our knowledge of real world H2O tells us otherwise. It actually exhibits a much higher, a significantly higher boiling point. So our question that we're going to focus on today is, why does H2O have that significantly higher boiling point? So let's go ahead and dig a little bit deeper into just water itself. So again, water is one of those molecules that's going to pop up over and over again in terms of having to draw Lewis structures. So it is really important to remember that even though you are tempted to draw it in the linear fashion, as I mentioned previously, group 16 atoms bond in such a way that they leave only the bottom and the left, or you could rotate that, could be top and the right. They leave two spaces right next to each other open in order to bond. So here we have our water molecule. Our chemical formula, H2O. Okay, type of bonds. I always like to throw in a little bit of review on these lessons just to really get you thinking. But types of bonds, we have H, which is a nonmetal, and we have O, which is a nonmetal, which means that we have a covalent bond. Okay, bond polarity, looking at whether or not it's considered polar or nonpolar. For that, we do want to compare those electronegativity values. Okay, and so H has a 2.2. Okay, and O has a 3.4. I might have just made that up. Okay, but either way, O is significantly more, excuse me, electronegative, and they don't have the same electronegativity, which therefore creates a polar bond. Molecule polarity is based again on the symmetry of the molecule and the overall distribution of charge. So if we look at our dipoles, our partial positives and our partial negatives, you'll note that our molecule is asymmetrical and therefore it is considered polar. Okay, it is a polar molecule. So again, based on what we already know, we know that molecules that are polar have these dipoles, right? The partial positive and partial negative, and therefore should experience dipole-dipole forces of attraction. But let's go ahead and just sketch that out again, just to make sure that we are clear on how we represent that force of attraction. So we have our two H2O molecules. Okay, and we need to go in and label our partial positives and our partial negatives. Okay, sorry, lost my screen there. Okay, so we have to go in and label those. So again, we have partial positives, partial negatives. Okay, and now we need to show our forces of attraction. So again, to show the force of attraction, that IMF, we are going to use a dotted line. This helps us represent something different other than the bond, which is the straight line. Okay, and our force of attraction is going to exist between here, right, our partial positive and partial negative. So this is our intermolecular force of attraction. Okay, so in order to kind of verbalize that, the partial positive of H in one molecule is attracted to the partial negative of the O in the other molecule. Okay, awesome. So pretty much up through there, this has been a lot of review, but let's dig in now as to why we see that difference between H2O and H2S in terms of their boiling points or their strengths of intermolecular forces. So taking a look then again at our molecules, again, I'm just going to re-sketch them here. We have our H2O, and we have our H2S. Okay, and from there, we again automatically see two polar molecules, both dipole, dipole, perfect, we're good to go, we're done. However, okay, if we look at the molar masses, again, we should see that H2O, which is 18 grams per mole, and H2S, which is about 34 grams per mole, okay? we should see that H2S theoretically should have a much higher boiling point or a stronger intermolecular force based on what we know about London dispersion forces. However, H2O actually has the higher boiling point. So what is the reason here? What is our reason for that? And so in order to investigate that, we do have to look at our electronegativity differences. So comparing those electronegativity differences, we have H and O, we have H and S, a 2.2, a 2.2, a 3.4, and sulfur, even though it's in the same group as oxygen, already drops down to a 2.6. It is a significantly lower electronegativity difference. So we have a difference of 0.4 for our sulfur, but we have a difference of 1.2 for our water. And so what is coming into play here is this massive electronegativity difference. And this becomes very important to us because this really large electronegativity difference means that it has a really strong dipole. Okay? And so hydrogen bonding, as I mentioned, is a specialty intermolecular force. Okay? It is essentially a dipole-dipole intermolecular force, but it is a very strong dipole-dipole intermolecular force. So let's go ahead and define hydrogen bonding. There are only, well, I was going to say, you might be like, wait a second, Miss Daly, how am I supposed to know if something has hydrogen bonding? The good news is there's only 3 bonds or 3, electronegativity difference or bonds that are going to have hydrogen bonding. So I'm going to give those to you. It's not something you're ever going to have to play a guessing game on. Okay, so hydrogen bonding is our strong and special force of attraction for molecules which contain the following 3 types of bonds: HF, HO, or HN bonds. Okay, so our primary 3 molecules for Regents chemistry that we're going to be kind of like seeing hydrogen bonding in is going to be HF, H2O, and H3. But I do want to point out that if you do have a molecule that contains an OH bond, then it still exhibits some form of hydrogen bonding as well. For example, if we have something like methanol, which again we'll focus on in our organic unit, but if you have something like that, that still does have that OH bond and does exhibit some hydrogen bonding intermolecular forces. Awesome. So now we've covered our 3 types of intermolecular forces: London dispersion forces, dipole-dipole forces, and hydrogen bonding forces. And now all we have to do is really kind of tie all this information together and see how it helps us relate back to boiling point. So what I want us to do is I want us to use these 4 molecules here, and I want us to go ahead and rank these molecules, or first go through, determine the type of intermolecular force, determine the strength of intermolecular force, and then rank them by boiling point. Okay, so we're going to do this really quick all together. So carbon dioxide, it is a non-polar molecule. Okay, hydrogen bromide is polar. Methanol is polar. And carbon tetrafluoride is non-polar. Based on that, we can now identify the types of intermolecular forces. Carbon dioxide is going to be primarily London dispersion forces. Hydrogen bromide is going to be dipole-dipole. Methanol, dipole-dipole, but it does contain that OH bond as I just mentioned. So we're going to call this hydrogen bonding. and carbon tetrafluoride, which is London dispersion forces. Okay, what I'd like you to do is I'd like you to go ahead and pause here just for a moment and try your best to now rank these in terms of the weakest intermolecular force to the strongest intermolecular force. So go ahead and pause. Okay, and hopefully you paused. Welcome back. Now, something that I don't know if I've explicitly stated, but I think I did in class. So our weakest type of intermolecular force, the weakest IMF, okay, is going to be our London dispersion forces. Okay, our strongest IMF is hydrogen bonding. Okay, which means that our in the middle, okay, is going to be our dipole-dipole. So from that information, let's now go ahead and rank our strength of these intermolecular forces. So our strongest IMF is going to be hydrogen bromide. So we're going to make that number 4, our strongest. Okay, or I'm sorry, not hydrogen bromide. Our hydrogen bonding methanol is number 4. Okay, our dipole-dipole is going to come in second then as our number 3, okay, because it contains the dipole-dipole. And now we get down to our London dispersion forces. And again, for these, you have to compare the gram formula masses or the number of electrons. I personally think comparing the number of, or the gram formula mass is a little bit easier. So carbon tetrafluoride has a gram formula mass of not 154, that is massive. So let's see, we have the 4 times 19, okay, which is going to give us 76 plus the 12 from carbons, that gives us 88 grams per mole. Okay, 88 grams per mole. And then we have our 44 grams per mole for our CO2. Okay, so the stronger the mass or the larger the mass, the stronger the intermolecular force. That makes this number 2, and that makes this the weakest number 1. Okay, from there, what we need to do then is rank them in order of increasing boiling point. So our weakest IMFs are going to have the lowest boiling point, and our strongest is going to have the highest boiling point. That means in order, we're going to have CO2 to CF4 to HBr, okay, to the methanol or CH3OH. All right, everybody, thank you so much for tuning in, and I will see you guys in class.